Now this question is given in GATE 2001. It is about the paging concept, single level paging. They are saying that consider a main memory with 64 MB physical memory, machine with 64 MB physical memory, which means physical address space is 2 power 64 is 2 power 26, right? 2 power 26 bytes, that is what they said. And the virtual address and a 32-bit virtual address space. So actually virtual address space should not be 32-bit. The question should have been virtual address is 32-bit. Anyway, that is the meaning of it. Okay, so virtual address is 32 bits, right? Therefore virtual address space is 2 power 32. If the page size, so they are saying that page size equal to 4 KB, which means 2 power 12 bytes. What is the approximate size of the page table? Right, so how can you find out? First you find out the number of pages, then depending on the number of pages you can find out the number of entries in the page table, and then you find out the entry size. What is the entry size? Entry size is nothing but the frame number, right? I mean the number of bits used to represent the frame. Okay, now how many number of pages will be there? See this, it is 32 bits and page offset is 12 bits. Therefore what will be the page number? Then the page number will contain 20 bits. So how many pages will be there? 2 power 20. You should be able to do it very fast. And after finding out the number of pages, that is equal to the page, number of entries in the page table, what will be the size of each entry? Each entry should be pointing to the frame number, right? So physical address space is 26 bytes, 26 bits, and page offset or frame offset is 12 bits. Therefore if you subtract it, how many bits are remaining? 14 bits are remaining. Then 14 bits are going to represent the frame number, right? So frame number is going to be represented using 14 bits, and this is the most important thing in the page table entry, right? Therefore page table entry is going to contain 14 bits. Let's say E. Then what is it? 14 into 2 power 20 is the answer, right? So 14 bits into 2 power 20 pages, that is the page table size. Therefore page table so page table size is number of pages into number of bits required, right, in each entry. So number of pages is 2 power 20 and number of bits required is 14. Therefore this is the page table size in bits, right? So which is nothing but 14 M bits. So it is 14 M bits, but the answer is given in bytes. So if we divide it with 8, it is nearly equal to 2 MB. They are asking approximate size, not the exact size. Exact size is this one 2 power 20 into 14 by 8 bytes, but then if you substitute in place of 14, if you substitute 16, you are going to get 2 MB. So approximate answer is 2 MB. Got it? Okay, that is about that paging. And this question is asked in I think GATE just check, let me check it. This question is asked in GATE 99. Okay, and now they are asking which of the following is or are advantages of the virtual memory. So they are talking about the virtual memory. So what is the main concept of virtual memory? Whenever the process size is larger than the available physical memory, then we are going to let the process stay in the hard disk, and only the part which is required we load it into the main memory and when run it. That is called as virtual memory, right? So now what is it? Which of the following is or are advantages of virtual memory? They are talking about virtual memory, right? Then how can we solve this question? Now read the options. First thing is faster access to memory on average. Using virtual memory, access will never become faster. If anything, it becomes slower. How? Because all the pages are not in the main memory, and whenever we want the main memory something from main memory, we are supposed to get it from the whenever the page is not in the main memory, we are supposed to get it from the hard disk, right? So for that reason this is not faster, it is slower, so it is not an advantage. And next one is processes can be given protected address spaces. It is called as protection. So protection is not the feature which is specific only to virtual memory. Even in the contiguous allocation also, we had protection. How? By having that limit register, if you remember it, base and limit registers we had, isn't it? So protection is not a special advantage which we get only by using virtual memory. Even by using normal memory concept also, even by using normal page table also, we can get it, right? So protection bits are always there. So this is not the advantage which we get only by virtual memory. This is already existing. And next one is a linker can assign addresses independent of where the program will be loaded in the physical memory. So this is relocatable addresses. They are talking about relocation. So relocatable addresses are given by linker even in the contiguous allocation too, even in the paging too, normal paging, right? So runtime conversion, or that dynamic conversion doesn't have anything to do with virtual memory. These concepts are already existing even in contiguous memory as well, right? So this is not a special advantage of virtual memory. Programs larger than the physical memory size can be run. This is the only advantage we have, right? And all the other things, they are already there in the earlier concepts. So by using virtual memory, I am able to do only this thing, right? So in some of the books, they are given some wrong answers about this. Only D is the right answer. They are given, I think, B, C or D, something like this. But only D is the right answer. Okay, fine.